This is the third shear and moment diagram example. And what you see here is basically you have a beam that's simply supported, but it has this little hook thing which is going to actually apply both a force and a moment along with a distributed load across the top. So let's see if we can figure this out. First off, let's start with doing a quick little rigid body analysis, which I'm just going to simplify everything, and then we'll bring it back to the original problem. You cannot run with this simplification. Don't try. This is going to be your AY. This will be your B, essentially just B. And then you're going to have 300, that'll be 10 pounds times 30, so 10 pounds per inch times 30 inches. This equals 300. You got to find the centroid of that distributed load, and that will equal, that's right in the middle, right over where the member is, this angled hook-looking member. So it will actually result in a 300 plus 400 pound force directly down in the center. So 400 pounds directly in the center. Plus there will be a moment due to this hook design right here, which will result in a moment in the positive direction of 500 pound-inches. Okay, so now let's just solve it the way we've always done it. Sum of the moment around A is going to equal, it'll equal 400, will be negative 400 times 15 plus B times 30 plus 50 pounds, or 500 pound-inches, right? Equals 0. And what you'd find is that B is equal to 183.33 pounds. If you use your sigma f of y, at that point you'll have A plus 183.33, that's your B, minus 400 pounds, equal to 0. You'll be able to solve for A at this point, which would be 216.67 pounds. And this is how we determine the effect of that rotation, or that moment, that little hook design at the bottom of the beam. So, knowing this, we can actually backtrack and work our way through the shear diagrams now. Let's draw our first one. Our first shear diagram is going to look something like this. Sorry if everything looks a little messy. Okay, so first off, we start with our force at A, which is going to be somewhere around 216.67. Okay? So 216. Then, what's the next important point? It's going to be halfway, right? At the halfway point, what is the moment going to be due to that? What is the decrease in shear going to be due to the distributed load? Basically, what I'm asking is, what's the total amount of force that's going to be applied due to that distributed load on top of the beam? And what you'd realize is that you've only gone 15 inches. So 15 inches times 10, that's 150 pounds. 10 inches, 10 pounds per inch. And 15 inches, it's going to be 150 pounds. So this will actually go down to near 66 by the halfway point. So this would drop down to 66. Which is great. I mean, 66. Then 66.67. Then at this exact moment we would drop 400 pounds. So we would be we would drop 100 pounds, 100 pounds due to the hook force. So this would be down to near negative 33.3. Then it would continue to put more force down until what next important point? It would be at the end, which would be the same value, which will be equalized out or brought back to equilibrium at 183.33. So we know that the ending point is going to be negative 183.33, because that is the force that has to bring it back. So you can kind of connect the dots. And what you realize is that your shear diagram is starting to look pretty interesting. Now, this is the shear diagram. If that is that complicated, what could the moment diagram look like? And I think you'll like this as well. With the moment diagram, I don't want you to think, oh, I gotta calculate this out intensely. I just want you to find important points and then rough it in between. So we know that, first of all, that this is going to start out at 0, and we know that it's going to end out at 0. We know that it's going to go up, and then it's going to peak, and then it's going to come down. We know that. So what does this mean? Well, if we came up with an area for just this part right here, this whole area of this first segment, we actually come up with something around 2125. So if I were to draw that at the halfway point, we would have 2125. And we know that it starts off faster because it's higher on the left side than it is on the right. So it actually starts off going upwards quicker, but then it slows down. Never flattens out though, so it does start off quicker. So it starts off something like this, but then it never ceases to go up. That's the concept. Then we get to this point. At this exact moment, more moment is added in to counteract this motion. So what we realize is that it drops us 500 because it was due to the hook shape. There was an actual moment that was applied, as you can see in our free body diagram from before, that is applied right in the middle. So that makes us drop down because some of that moment is counteracted by the 500 moment that's caused by that hook shape. So now we're actually at 1625. At which point we would continue until it hit 0. And as you realize that it never stops decreasing, and it actually gets quicker and quicker at it. So what you'll realize is that it's something along this line. Continue, and it gets quicker and quicker and quicker. So it looks something like this. And I know it looks kind of funky shape, and you couldn't really tell, you couldn't say that I plotted this point by point accurately, but you can say that this is the general shape of this diagram, and you can see where the peak is. The peak is right at 2125, and it's really just a good tool to use to allow yourself to develop, I guess, a more intuitive approach to beam design and how to lay out the supports. So anyway, I hope you guys have a good day, and leave any comments if you want some more problems or whatnot.